All right, good afternoon, everyone. We are going to talk today about homework number 10. And for this one, you have to solve problems related to hydraulic fracturing in field tests. The first example is an example of a leak-off test. So, for this example, what we're going to have to do is to interpret what is the minimum principal stress and what is the type of faulting regime based on all the data that we have over there. So this is not like a cookie cut type of problem, right? You have to see all the data available, and then you have to solve it based on the knowledge that you already have. And in this one, we have data of depths. You see water depth, you see total depth up to this point, and you have here now a leak-off test. So what you have to do in this case is to interpret this data with these depths and answer all of these questions. The first one is the easiest one. And let's start with that one. Compute what is the vertical stress at this place. Okay? And here you have some data that's going to help you, and you can assume typical gradients. In order for us to get all of us the same answer, let's assume 0.44 for the gradient of pressure in the water section, psi per foot, and then 1 psi per foot until the total depth. Okay? So that's going to be the first step to compute SV, and then we're going to use the plot. Okay? So that should take you less than 1 minute to compute SV with those values, and you tell me what the answer is. Okay? And in the meantime, I'm going to get this on. And this is actually real data, guys, okay? So we're going to see how what we learned so far, it helps explain what happens in reality. Yes?
Do we assume the seawater is 0.465 and then 0.44 feet? Or
So 0.44 for the water section, and then just 1. We're computing total vertical stress. Okay? Anyone has already the answer? 6,447 psi. Everyone agrees with that? Okay. So now that we have that data, let's see this example, and just look at the downhole pressure. Okay, I'll talk about the surface pressure in a bit, but just look at the downhole pressure, which is the black line. What do you think is going to be, according to this plot, where I'm telling you already where the fracture closure is, what is going to be the downhole pressure at that point? Let me help you a little bit. We're going to use this as a ruler. and it's that value over there, right? So what is going to be the fracture closure pressure? Yeah, let's say 5,240, okay? So I know that now S3 is 5,240 psi. So if that's the case, then what do you think the type of faulting regime is? Could it be reverse faulting? Why not? It's less than SV, right? So it's not reverse faulting. It's either strike slip or normal faulting. So we can discard that option. Well, now knowing what is the pore pressure, please go ahead and calculate sigma V and sigma 3. And in the meantime, I'm going to pull up the dog camera. So I'm asking you to calculate now sigma V and sigma 3. And since we already know that this is either strike slip or normal fault, or normal faulting, then that sigma 3 is going to be also sigma H mean. Sorry about that. So this is what we have done so far. All right, so you already have the value, those two values. I'm not gonna write them, so because you have to do the homework also at home. So here you're gonna get sigma H mean, and here you're gonna get sigma B. And now the next step is to compute the anisotropy ratio, sigma B divided sigma H mean. And I'd like that you tell me what that value is. 2.24? Okay. So 3.24. And based on what we have seen so far for typical values of the maximum stress anisotropy, do you think that's close to failure or far from failure according to typical values of Q? It's very close, right? When it approaches an anisotropy of 3, that means it's very close to failure.
Wait, so this one's a little bit more than 3, does that mean?
No, that's okay. That's okay because we still there is quite a bit of variability. It doesn't have to be exactly 3. So if this one is already close to 3, that may point to the fact that very likely, what is the type of faulting regime? Why normal? Because it's the largest stress anisotropy, right? There might be a stress anisotropy which is similar on the other direction for sigma H max, but But we don't know. We don't know about that, at least from the data over here. You had a question?
So in the notes it says typical values of Q range anywhere between 3 and 7. So like when we say that the stress anisotropy is like close to 3, like is it safe to say that it's close to failure? Because I mean if it's like 5 or 6, then it can be close to failure then too.
Well, there is something that it reminds me now a little bit of the exam. Typical values of Q go from 3 to 7 when you account for the internal strength of the rock. So that's the Q of the intact rock. But usually the Q of already broken material and of faults especially tends to be a little bit slower, a little bit lower than that. So closer to 3.
And could you also explain one more time why it should be normal faulting and not strike slip faulting based on Q?
Because it looks like if I'm stating this, I know that the stress anisotropy is already quite large comparing sigma phi and sigma h mean. So if I had more stress anisotropy with another stress like sigma h max divided sigma h mean, that would have to be larger than that. And if it's larger than that, it would be 4 or 5. That would be not very likely because this is already a quite big, large anisotropy.
Okay. So if the anisotropy was lower, then the anisotropy between H max and H min would be high, which would be
Correct. Yes. So what I'm saying is that also here, very likely, sigma h max divided sigma h min is less than 3.24. And why? Just based on typical values of stress anisotropy observed in nature. Okay, so I have one more problem for you to solve. It's I want you to tell me what is the density of the drilling mud. How are we going to get this one? What we have to do is to use a reading of the downhole pressure before you start injecting. Here in this problem, it's not super obvious that injection starts here, but you see how this value is more or less constant, and then it starts to increase. This is the point where injection starts. So at this point, the drilling mud it's at hydrostatic equilibrium. So with this pressure and that depth, you can tell me what is the density of the mud. Okay?
And that's about 4,700 psi.
Yeah. Let's assume that value, 4,700. Yes.
What's that little pig that you gave me?
Say again?
That little pig, stick out a little bit to like around 4850, and then it goes down.
This thing?
Yeah.
Well, this is the surface pressure. The surface pressure, apparently, when they were doing some connections, the pressure went up a little bit, 100, 200 psi. But you see the downhole pressure, it barely moves. So let's finish this problem and then we'll talk about the surface pressure. Okay, because here you have the two readings, the surface and the downhole pressure. So in our previous problems of wellbore stability, many times we calculated the wellbore pressure, and with that we specify mud density, right? This is sort of an opposite problem in which you know what is the wellbore pressure, and then you need to figure out what the mud density is. Anyone got the value for that? 11.05. And does that make sense to you?
Yeah.
It's a value that makes sense?
Yeah.
So the units and the units that you are giving are pounds per gallon, right? So yeah, that makes sense to me as well. Okay, so from this data we can get that value. So let's see what was the objective of this paper? Many times in most of these field tests, you do not measure the downhole pressure, but you measure the surface pressure. It's much easier to measure a surface pressure than a downhole pressure. But the actual pressure in the wellbore or in the fracture is going to be the downhole pressure. So in order to interpret what is the downhole pressure from the surface pressure, we have done the assumption that that's going to be just the additional column of fluid in the wellbore plus a surface pressure reading, but sometimes that's not exactly the same. The procedure is not exactly like that. You need to add some viscous forces, and you need to add some other things that are going to make that reading a little bit different. So what is shown in this plot is that surface pressure reading, which is the red, and the downhole pressure reading are a little bit different, and that can give you sometimes some uncertainty about what the actual value downhole is, but most times they are fairly close. So the takeaway message from this is that sometimes we need to calculate downhole pressure in order to know stresses, but most times you do the measurements on surface. So in order to know the downhole reading, you need to add always the column of fluid in the wellbore, okay? And that's going to be the next example that we're going to see. All right, so for those of you that brought your computers, you can go ahead and click over here, and you will see that link will take you to a text file. In this text file, we have data of time, pressure, and injection rate. And if you download this file and you plot pressure and rate as a function of time, which is actually the first part of the problem, you're going to be able to see those two variations, the one of pressure and the one of rate. So please go ahead and do that. And the first thing I want you to do is to plot pressure as a function of time and injection rate as a function of time. You should obtain something very similar to what I'm going to show in a bit over here.
Can I plot in the same graph or no?
Yes, please use the same graph with two vertical axes. You know how to do that, guys? If you don't, probably this is the chance to learn how to do that. If you need help, let me know. But basically what you do is you first plot the two of them with the same axis, and then you go to one of those data sets, you do right click, and then you say something like put on secondary axis or something like that, and that's it. So okay, you're gonna see something very similar to this. So here you see you have the two axes, and one is for surface pressure, the other one is for rate. And again, if you put it in a secondary axis, then you can adjust these two axes to show the plot more or less in the same scale. And if you are fancy as I am with these plots, you can also change the color of this axis so it's easier to read which is rate and which is surface pressure. And after you do that, I'm asking you to make a zoom of that region, okay? So I'll give you 5 minutes to work on that, And people that didn't bring computers probably can start working on the following problem. Which is a similar problem, but it doesn't involve the use of a computer, okay? This one, number 3. So let me know if you need any help, okay? So if you notice in some of these plots, the pressure goes directly into a flat trend. So it appears that in this case you don't have to go over a hump in order to achieve the fracture propagation pressure, but it just goes directly into that pressure. Did you guys get to plot the data?
The secondary axis again?
Go to the data and let me see if I can do it here quickly. Press the right button, and there you will see something that will say add to secondary axis or put on secondary axis or something like that. So okay, no, I didn't like that. Let me see, I don't want to. Okay, let me just do a quick demonstration here. Did you get it?
Yeah.
Okay. So there you have the two plots, right? And if I get this one, I click the right one, and then you go to format data series, right? And then secondary axis. There you go. And then what I was telling you is that in order to make this easier to read, I like to change the color of that so it matches the color of the line. Okay, so after you do this plot, I'm asking you to find what is the instantaneous shut-in pressure and the instantaneous shut-in time. It may not be super obvious from here, but it's going to be much more obvious in the second step. So remember, this instantaneous shut-in pressure is the highest pressure right after the pumps are shut and the pressure starts to decay gradually. So now this one is a very abrupt decay, but when it starts to decay gradually, the highest pressure, that's going to be the instantaneous shut-in pressure. After you find that point, you're going to have to add one more column to your data. So let me go to the data. So what I would do here is, here you have time, you have pressure, you have rate. After you have the instantaneous shut-in time, you're going to have to create a new time column where the 0 starts at the instantaneous shut-in pressure. And of that new column, you take the square root of that. Okay? Let me save this file. I'll see if I can do it quickly here. Where is the download button here? I think this is the hardest problem of the homework. The other ones are pretty easy. All right, let's see. Okay, so I have the data there. I think you already did what I told you before, but I'm going to do it again. Pressure, rate, okay. Tell me, what did you find as the instantaneous shut-in pressure? 20, but the data starts at 70.
The pressure.
And what about the time? 70, 73? Okay, so 73.3 you said?
Yeah, 73.3.
Okay, let's assume that this is instantaneous shut-in pressure. Then what I'm going to do is I'm going to create a new zero here. And calculate the square root of that. And now I have a new axis. And now what I'm going to do is I'm going to plot this. And you should get something like that.
Professor,
Yeah.
What was your equation? Did you just set 0 for that 73?
Yeah, I made this my new zero. So now this is going to be time, we call this shut-in square root. And wait, there's something funny here. Let me see what's going on. Are you sure it was 73? Okay, let me check that. Because from here it looks like it's taking some of those points in here. So you guys, you all got 73?
73.26.
Well, you see, I put the mouse here, it tells me 73.66.
Yeah.
Okay? So let's try with that one. I'm going to have to move it. It's going to be this one is going to be very obvious what is the actual instantaneous shut-in pressure, because when I plug the gain, now you see how I have a plot here. Let me make a zoom. In the beginning, probably that was too much. Okay, so you see how that point, it looks quite further off from that one. And we'll make a zoom now on the y-axis. It's going to allow us to see a little bit more what's going on in there. Okay, and I'm going to go here to 5. And you see how it looks like there is a very nice line over here, but that point is not in the main trend. Well, it looks like instantaneous shut-in pressure is here rather than there. So let me correct that. Let's take a look at that again. Come on. Okay. So let me pick the corner. Okay, it may be even a little bit, we could discard that point either. But now with this trend, we can see very clearly how the pressure goes down proportional to the square root of time in the x-axis, and then it starts to deviate at some point. So somewhere over here, you have to pick up what is the fracture when the fracture closes, and that's going to be the fracture closure pressure somewhere over here, and this is going to be the fracture time, the time at which the fracture closes. But notice that here you are in the square root, okay? So let's say that this is, I don't know, 1.7, then 1.7 over here corresponds to that time, okay? Important thing though here is not the time, it's the fracture closure pressure that you can read it, which is going to be somewhere in between these two values. So I'll let you pick exactly what the value is, okay? But I'm going to move on to the next part, which is knowing what that value is. That's a surface reading. It's a surface pressure. And knowing that this is the true depth for that test, and that we have a fracturing fluid with a density very similar to water, I'd like that you tell me what is the minimum principal stress. How are you going to obtain this? By adding the surface pressure reading to the column of fluid that you have in order to get to this depth. And that's going to give you the minimum principal stress. Okay? So please go ahead and calculate that one. And if you have the value, just let me know. Yes?
So, you said that the fracture closure happened at the inflection point when the slope changed sign, or when the slope was like almost non-linear?
Let's look at that here. It's going to be a blow very similar to this one.
Okay, so when it stops being linear.
Yes. So it's going to show a linear trend, and in that period the fracture is open, fracture pressure goes down very quickly, but when the fracture closes, you have less area for the fluid flow to leak from, and the pressure starts to go down more slowly. This is the point of the fracture closure pressure, and here the time of the fracture closure, which in this case we don't need that one, we just need a fracture closure pressure. And now this is a surface reading. This is the pressure that you need in addition to the one that already exists hydrostatically within the wellbore to open that fracture. So add that column, the pressure that gives you that column of fluid, plus the fracture closure pressure, and that will give you the minimum principal stress.
You say and once?
You need to add the pressure that results from the column of fluid that goes from the surface to the depth at which this test was performed. And here you have the data. This is the true depth. You have the depth, you have the gradient, you can calculate the pressure. That's going to be the hydrostatic pressure. But in addition to the hydrostatic pressure, you have pumps on the surface that increase the pressure so that it can make a fracture. So in this case, what do you guys get for 0.44 times 7,503? Did anyone already compute that? So this is what you need. This is the hydrostatic pressure within the wellbore. Don't get confused. This is not pore pressure. This is hydrostatic pressure within the wellbore, or within the pipe and the casing, which is moving the fluid into the formation, and this is the fracture closure pressure. Okay, and this is the surface reading. You raise your hand? No? Okay. So now with this equation, now you can calculate what is the minimum principal stress. The third problem is very similar, but now you have data, and here you see that this is the flow rate, more or less constant. After injection starts, pressure goes down, goes over the hump, then it goes into fracture propagation pressure, and then it decreases. Here I'm just asking you to point to, in the right order, I'm not asking specifically to pinpoint which pressure, but I'm asking you to tell me where do you think more or less the instantaneous shutting pressure is and the fracture closure pressure. And I don't remember if I asked for the fracture propagation pressure. Yes, also fracture propagation pressure. So fracture propagation pressure, instantaneous shutting pressure right after you stop injecting, and the fracture closure pressure after that. I'm not asking you to tell me exactly where that is with this data, okay? That fracture closure pressure. But it should be after the instantaneous shutting pressure and somewhere around here. And I think I'm asking you a few more things. Calculate how many barrels were injected. This is just basically reading the plot. You have flow rate, you have time. You can calculate how many barrels were injected. And also to calculate minimum principal stress, knowing that what is the bottom hole pressure before injecting. So you have the bottom hole pressure, you have the additional surface pressure needed for fracturing, you can calculate the minimum principal stress. Something I wanted to mention, and I didn't hear, is that notice how in our examples we say that fracture propagation pressure sometimes goes into a constant value, but that's not true. Sometimes it goes down, some other times it may go up, especially if it's a long fracture. But notice in these two cases of real data how the fracture propagation pressure starts to go down with constant injection rate. This one goes down, in this one goes down too, slightly. Okay, so we're just then going to skip this one. It's a simpler version of the previous one, but something that is easy to solve, for example, during an exam. Okay? All right, so the last problem of this homework is about the step rate test. And for this one, what you're gonna have to do first is to plot pressures as a function of time. So unfortunately, this is an image, okay? I didn't have time to put this into a table that you could copy and paste. So you're gonna have to type some numbers, and unless you do some sort of OCR algorithm and you pick up those values from the image, you can do that too. But what I want you to plot is pressure as a function of time. This is the first step of a step rate test. During this first step, the injection rate is constant, and as time passes by, pressure increases. What I suggest that you do is that you take this as your absolute zero, and then for the next step, you take this zero as 30. So this is going to be 30, 35, 40. This one is going to be 60, 65, 70, 135, 160, but it's going to be in minutes, right? You want to convert it. If you just keep it in minutes, this is going to be, no, okay, let's come back. I'm adding incorrectly. 30, 60, 90, 120, 150, 180, okay? And if you plot all of this pressure as a function of time, you will see how these pressures increase like a staircase, but they go into more or less constant values after some time. From there, you have to pick up the highest pressure in that interval and then plot the highest pressure versus injection rate, and you will be able to select what is and to find what is the injection parting pressure and parting rate. Mr. Ko, you have a question?
So at time 30 minutes, you have two pressures.
Yeah, you could say that, but it's going to show sometimes the highest pressure from the previous interval is going to be a little bit higher than the previous one, but it's going to be a plot that it looks something like this. It increases, it gets to a value, and the next one is going to start like somewhere over here, but it's going to increase over the next one, and so on. Okay, so yes.
How will we plot two y values to one x?
But you can do that, and there's no problem with that. Just you have two columns, right? Or two rows. So you will have one row that will say 30 and 110, and the next row is going to say 30 and 88. You see what I mean or not? So this is x and this is y, right? Okay, but this one is also going to be x and it's going to be y. But it's just put all the data together and you see how it nicely line up. It's not going to line up exactly the last point with the first point, but that doesn't matter.
So we will have, what, 7 plots?
But put all of them together in the same plot. And once you're done, as I was telling you, plot the injection rate versus the maximum pressure, and you will be able to get a plot that looks more or less like this. And then by plotting pressure as a function of rate, and you will recognize two regimes, and where those intersect, that's the formation parting pressure and formation injection rate. All right? Okay, so have a good weekend. Happy Easter for those of you that are, what?
Oh, wait, are those the exams that you have?
Yeah, but they're not ready yet.
Oh.
Yeah, I have to grade the last problem. Okay? All right. Well, see you guys. Take care.
I'm gonna cry.